In this video, we will talk about Top 10 Basic Principles of Physics. Physics is the study of matter, energy, and the interactions between them. It helps us understand how the world works, from the smallest particles to the vastness of the universe. Here are 10 fundamental principles that form the foundation of physics, explained in simple terms. 1. Newton's laws of motion. Sir Isaac Newton's 3 laws of motion are essential for understanding how objects move. First law, law of inertia. An object at rest stays at rest, and an object in motion continues in motion at a constant velocity unless acted upon by an external force. This means that if nothing pushes or pulls on an object, it won't change its state of motion. For example, a ball will not move unless kicked or thrown. Second law, F equals ma. The force acting on an object is equal to its mass times its acceleration. This means that heavier objects require more force to accelerate at the same rate as lighter ones. For instance, it's easier to push a bicycle than a car because the car has more mass. Third law, action and reaction. For every action, there is an equal and opposite reaction. When you push on something, it pushes back with the same force. This principle explains why you move backward when you push off the ground with your feet. 2. Law of Universal Gravitation. This law, proposed by Newton, states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. Simply put, the force of gravity pulls objects towards each other. This explains why apples fall from trees and why planets orbit the sun. 3. Conservation of energy. The principle of conservation of energy states that energy cannot be created or destroyed. It can only change forms. For example, when you lift a book, you transfer energy from your muscles to the book as gravitational potential energy. When you drop the book, that energy converts into kinetic energy as it falls. 4. Conservation of momentum. Momentum is a measure of how much motion an object has. It's calculated by multiplying an object's mass by its velocity. For example, if you throw a ball, the speed at which it travels depends on both how heavy the ball is and how fast you throw it. The conservation of momentum is a key principle in physics. It means that if no external forces are acting on a system, like friction or air resistance, the total momentum of that system stays the same. This is true even if the objects within the system collide or interact. Think of 2 billiard balls colliding on a pool table. Before they hit each other, each ball has its own momentum. When they collide, they transfer momentum between each other, but the total momentum of both balls combined before and after the collision remains unchanged. This principle helps us understand how objects move and interact in a predictable way, as long as we account for all the forces involved. 5. Thermodynamics. Thermodynamics is the study of heat and energy transfer. First law of thermodynamics, energy conservation. Energy cannot be created or destroyed, only transferred or converted from one form to another, similar to the conservation of energy principle. Second law of thermodynamics. Heat naturally flows from hot objects to cold ones, and not the other way around. This law also introduces the concept of entropy, which measures the disorder of a system. In simple terms, over time, systems tend to become more disordered. Third law of thermodynamics. As temperature approaches absolute zero, the entropy of a perfect crystal approaches zero. This principle helps us understand the behavior of systems at very low temperatures. 6. Electromagnetism. Electromagnetism studies the interactions between electric and magnetic fields. Coulomb's law. This law describes the force between two charged objects. The force is attractive if the charges are opposite and repulsive if they are the same. The strength of this force decreases with distance. Faraday's law. This law states that a changing magnetic field induces an electric current in a conductor. This principle is the basis for electric generators and transformers. Ampere's law. This law relates the magnetic field to the current that produces it. It helps us understand how electric currents generate magnetic fields. Maxwell's equations. These four equations combine all of electromagnetism's laws into a unified framework, describing how electric and magnetic fields interact and propagate. 7. Quantum mechanics. Quantum mechanics explores how very tiny particles, like atoms, and those smaller, behave. Unlike classical physics, which deals with everyday objects and their predictable movements, quantum mechanics reveals some surprising truths. For instance, it introduces the idea of superposition, which means particles can be in multiple states at the same time. Imagine a coin spinning in the air. It's not just heads or tails, but both until it lands. Another key idea is entanglement, where particles become connected and can instantly affect each other, even if they are far apart. This is like having two magic dice that always show the same number, no matter how far apart they are. Quantum mechanics also shows that particles can act like both waves and particles. This wave-particle duality is different from classical physics and helps us understand the strange and complex behaviors of particles at the smallest scales. 8. Relativity. Albert Einstein's theory of relativity has dramatically changed our understanding of space and time, dividing into two main parts, special relativity and general relativity. Special relativity. This theory, introduced in 1905, revolutionized physics by asserting that the laws of physics are the same for all observers moving at constant speeds relative to each other. One of its key principles is that the speed of light in a vacuum is constant, no matter how fast the observer is moving. This idea led to the famous equation E equals m², which shows that energy E and mass m are interchangeable and related by the speed of light squared, T2. Essentially, this means that mass can be converted into energy and vice versa, which has important implications in both physics and technology. General relativity, proposed in 1915. This theory expands on special relativity by incorporating acceleration and gravity. Instead of treating gravity as a force, general relativity describes it as a curvature of space-time caused by the presence of mass. Imagine space-time as a stretched rubber sheet. Massive objects like planets and stars create dents or curves in this sheet, and objects move along these curves. This theory explains why light bends around massive objects, a phenomenon known as gravitational lensing, and has been confirmed through various experiments and observations. Both parts of Einstein's theory of relativity have been essential in modern physics, shaping our understanding of the universe's fundamental workings. 9. Wave-particle duality. Wave-particle duality is a fundamental concept in quantum mechanics that describes how particles like light can exhibit both wave-like and particle-like properties. To understand this better, let's consider light. On one hand, light acts like a wave. For example, when light passes through small openings or around obstacles, it creates interference patterns. These patterns, where light waves overlap and create bright and dark regions, show that light behaves like a wave. On the other hand, light also behaves like particles, specifically tiny packets of energy called photons. This particle nature is evident in the photoelectric effect. When light shines on a metal surface, it can knock electrons off that surface. This effect demonstrates that light doesn't just spread out like a wave, but also transfers energy in discrete packets, or particles, to the electrons. This wave-particle duality is crucial for understanding the behavior of particles at the quantum level. Unlike everyday objects, which clearly behave as either particles or waves, quantum particles like light can show both types of behavior depending on the experiment. This duality challenges our usual perceptions and helps explain the complex and often non-intuitive behaviors observed in quantum physics. 10. The Standard Model of Particle Physics. The Standard Model is a theory that describes the fundamental particles and forces in the universe, excluding gravity. It classifies all known subatomic particles into quarks, leptons, and bosons. Quarks combine to form protons and neutrons, while leptons include electrons and neutrinos. Bosons, such as the photon and the Higgs boson, mediate fundamental forces like electromagnetism and the weak force. Understanding these principles provides a solid foundation for exploring more advanced topics in physics. They offer insights into how objects move, how energy is transferred, and how fundamental forces shape the universe. What do you think of our video? Let me know in the comment section below. If you enjoyed this video, make sure to hit that like button. Also, subscribe to our channel before you go. Thank you for watching.